On to one of my favorite topics, exponential growth and decay, because these are real world kind of things. You see these things here. I alluded to it in my last one, in 7-6, when we talked about the growth on the graph, like the growth of the bugs, that kind of thing. So that's kind of what we're looking at here. Exponential growth has a very specific exponential function. So the initial amount, so this is important that you know this. It's important that you know this A right here, the number there, the constant, right, is always represents the initial amount. Because if I have whatever the B is to the 0 power, that's 1. So 1 times this, that's what you start with. At the time that you start with the problem. You could technically go back in time in these cases, so it can lower this amount. Obviously, the whole thing can't become below 0 when it comes to a population kind of thing. And then here, this is the base. B has to be greater than 1. Growth factor equals 1 plus the percentage rate of change expressed as a decimal. So that's right here, that's important to note. And again, obviously the exponent, the function of the growth here. So, I'm sorry, that creates the growth function. It's important to note you should memorize what this looks like. Okay, knowing this is really, really, really important. So to clarify, exponential growth can be modeled by, again, this function, where A is greater than 0 and B is greater than 1. And because if A were smaller than that, things would shrink, right? So, or I'm sorry, bigger than 1, A is bigger than 0, I'm sorry, because it, you have to start out with a certain population. You can't start with a population of 0 things. And B is greater than 1 because you have to have a growth factor, not a declining factor, right? And again, there that looks like, and if you recall, here's our function graphed rather. So this general growth from however small a population you started with, going all the way up, and then notice how quickly it grows after a certain point. So to provide an example for your vocab, if you'd like, right here. So if I plugged in, I start with 360, and here we have that factor of 1.07 raised to the x power. After 10, whatever this is, weeks, whatever, here's the number we're going to get. It's about 708. So maybe this will work an example in your vocab. Another way to use this is compound interest. Kind of fun. A lot of stuff you're going to want to know here. A payment on both principal and interest. Okay, so compounded interest, that's a definition. In this formula, A is the balance. That's how much money you have. P is the principal. That's what you started with. Kind of like the A in the last one, the small a, right? Here, R is the annual interest rate expressed as a decimal. So notice annual. That's extremely important. N is the number of times of year it's compounded in a year. So if I say it's compounded every 6 months, right? That'd be 2 would go there. If I say it's compounded once a year, that's a 1 that goes there. And then the whole thing is raised to the NT. Again, that same N here, so it's used twice. And T is the time in years. So it's important that we understand P principal, R is the rate expressed as a decimal, the annual rate. That's very important. I've stolen this example here for your vocab. Compound interest, you can see here how it's used. So if you start out with, it says, suppose that when your friend was born, your friend's parents deposited $2,000 in an account, paying 4.5% interest compounded quarterly. What is the account balance after 18 years? Notice compounded quarterly, so that's 4 times a year. I'm going to write that here so you don't forget that. 4 times a year. Now, 4.5% is a decimal. 0.045. Okay, I know there's a decimal in this, but that's not what I mean. So let's take a look down here. We certainly have, first off, the P, the principal. That's how much you started with. 1 plus, again, the rate there, 0.045. Over N, that's 4 times a year. Raised to the N, that's 4 times a year, times the T, time in years, 18. So remember our rules here, 4 times 18 is 72. I'm going to go ahead and divide this out, 0.045 divided by 4. Add the 1, that creates this decimal inside. Raise this to the 72nd power, multiply by 2,000. After 18 years, he would have $4,475.53. Again, that's assuming he started out with $2,000 after 18 years. That'll serve as your example, by the way, for compound interest. Exponential decay is a very similar formula. Notice here the A, B, X stuff, right? Initial amount here, X, when X is 0, right? This is all you get. So after 0 time, with respect to decay. Now, I think you guys might have talked about this in science. You talked about radioactive decay, right? So there's a formula for it. This is a thing people really use. So the base is between 0 and 1 this time. Okay, that's how it's going to get smaller. If it's bigger than 1, you have growth. Less than 1 gets smaller. That's a test question, by the way. I just said that, so hopefully you're paying attention, right? So again, if this is bigger than 1, growth. Less than 1, right? Decay. Exactly 1, nothing happens. So again, decay factor is 1 minus the percentage rate of change expressed as a decimal. Serving here as an example, exponential decay. Again, it's going to, the other graph went up in this way. This one comes down. It grows towards 0. Theoretically, never can reach 0. I mean, unless the last one dies or decays, whatever. But you always have that half-life kind of idea, and I'm sure you guys talked about that in science. So anyway, it can be modeled by the function. Again, with the decay factor, that's B, the base is the decay factor. So here, again, initial amount, decay factor, raised to the exponent. That's our, help us determine time. Nice example here, and I think we're going to go over this one in our actual examples in a little bit. But here it says that we have a unit of measure for atmospheric pressure. The atmospheric pressure at sea level is about 101 kilopascals. Hey, I got that right, kilopascals. For every 1,000 m increase in altitude. So you go up, and the pressure goes down. So it's an inverse relationship. The pressure decreases about 11.5%. What is the approximate pressure of an altitude of 3,000 m, right, meters? Okay. So again, exponential decay function. X is the altitude. Y is the atmospheric pressure in kilopascals. Fun word, right? A is the initial pressure, and B is the decay factor. Again, 1 minus this 11.5% goes right here is 0.885. That's where that comes from. This is on my quiz and test, by the way, people. You got to know these parts. So Y equals 101 times 0.885 raised to the X. And again, we want to find out after 3,000 meters of going up, it's going to be about 70, right, kilopascals. I'm just going to round there. And we'll work about this bond at the bottom in a little bit.